Yeah, I'm Ren Wu, a distinguished scientist at Baidu. So if you cannot find me or if you rush to the party, so my email is there, so you can always send me emails or find me from LinkedIn or even from Chinese website. Yeah, I think NVIDIA definitely knows the old way of saying things, and you save the best to the last, right? So I think they really get the point. And who did go to party anyway? So I will take 90 minutes time. So we're talking about more interesting stuff. Well, today my talk is really the deep learning and high fashion. So, well, this has gone viral last a few weeks ago. I think everybody probably know already what color is this. But I put this example is because, believe it or not, our deep image system that was developed last year have this so-called color constancy capabilities built in. I will show you what we have done and why we can get there. So just put this aside. And before I go to more, well, this is real truth, but let's put that aside. Before I go to next slide, look at more dresses. I was asking, when I gave a presentation in different conference, I was asking the audience who you prefer, left or right. The interesting answer was from the audience, of course, the gentleman said, no, we like both. And the lady said, we like neither, none of them. So I like to ask this audience, who you prefer, which one you like more, left or right? I will give you our answer later, but let's go to the real technical discussings. So this was the presentation I did last year. So I was have two formulas. And you have big data, you have deep learning, and you have high performance computing, so you get better intelligence. And once you have that better intelligence, again with big data, deep learning with heterogeneous computing, and you deploy that intelligence everywhere, that's where we call success. But today, I will actually scale back to talk about more the first portion. It's really the intelligence part. So that's what we did to push state-of-the-art image recognition. I think deep learning has been popping up for the entire conference. I don't need to give more introduction, but that's something happened for Baidu's stock. The reason for that is because our CEO openly stated that deep learning is the key secret source. That's why our stock price jump like crazy. Everybody else should do the same to push your stock up. Well, big data, everybody knows this is one of the enablers, because we now be able to collect in much more data, we'll be able to process in much more data, and also in the meantime give much more data to train our neural networks. But for us, or for me at least, I think there is even more important driving force behind. That was the computational power. Back to my previous life, I was doing computer chess. If you draw this chart, you see the big blue line is the world's best personal computer chess programs. And the chart downwards is the MIPS of the chips. As you can see, there's two assembled very, very well. Basically, computer chess world tell us computational power is the driving force for performance. For me, being working in a computer chess community for so long, I actually see this happen in deep learning. What I like to see is really history is repeating itself, because right now deep learning is computational power. How much computation can you put, can you use, can you to crunch to those data to get better results? Of course, all know in 1997, Deep Blue beat Gary, so that was a historical event. And back to what Deep Blue guys, or Christopher Xu he did, was a classic example to build a customized supercomputer dedicated for playing chess. What we did is basically the same thing. Instead, we built a supercomputer dedicated for deep learning training. And this is another slide to just show how dramatic the computational power has increased over the time. Because I don't have enough time, because I do want you to go to parties, so I will go fast to skip this one. So For Baidu, we have so many deep learning-based applications being already deployed online, serve billions of the users. In this case, I will focus on image recognition. That has been, again, in the hot topic in this conference. So we will focus just for one particular case, which is the ImageNet computation. In previous speaker already gave a very nice presentation that over the years, this computation, starting from 2012, that where Alex showed that deep learning can be used for the computer vision, for the ImageNet computation in such dramatic way, things has changed or has gone a far way. As you can see, last year, Google's results was 6.67% error. That was a stunning result, and even New York Times have an article about this performance because that is almost superhuman performance, even though that's still not in the human performance just yet. Is this invincible, or is this result? Well, of course, not everybody knows, but back then, that was the question I think most people was asking, can we further improve that results? For us, luckily for Chinese, we got some inspiration, or our mastermind in Asian Chinese already point out the approach for us. For example, Shunzi, which is studied by Western culture in depth as well, pointed out a long time ago that more calculation is better than less calculation. More calculation wins, less calculation loses. And also another mastermind, Baidu, he basically saying that the more you see, the smarter you are. Finally, Mengzi, the Memphis, he pointed out that really smartness depends on how much the fine details can you observe, can you watch. Those are the inspirations for our work, and I will explain one by one what we did, why these principles is actually have impact to our work. The first thing is really we want to, again, push the computational power to do more calculation according to Shunzi. The first thing we did was really design a supercomputer. As you can see, we get the inspiration from all the methodologies from Chinese and Western. And we want to get this machine so that we can use it to maybe brew a new kind of intelligence. A core point is we do hardware and software co-design. In other words, this is not a computer you buy from off the shelf or you order from some companies, then you put your software in. What we did was we want to do deep learning training, and we know the calculation is important. We know the computational power is the driving force. We really want to optimize across the board to do the maximum optimization possible. And in total, this machine has 0.6 petaflops of the theoretic peak performance. And this is one of the photos we took. So we also optimize the software in a great extent. In our case, 32 GPUs will give us 25x performance compared to single CPU. Sorry, compared to single GPU. And this is wall clock time. In other words, this is a time that the training converge into certain accuracy level. So this is the most rigorous measurement can do for the parallel software. And again, we show tremendous performance gains by doing this customized design and customized software optimization. Now come to the more interesting parts. We ImageNet have 1.2 or 1.5 million images of the training samples. That seems to be a large, but when you scale your network, because we want to really build a huge neural networks, that samples just insufficient. So we always seeking to augment the samples, to make more samples even. There is two observations in this work, which was not widely known before or not done before, was one. The first one is we want our models to be invariant to the nominal of the thing. So that's where, back to the first picture, the address issue. Because human brain, over the years, the involvement have develop so-called color constancy, because different light source, largely human brain will see the same color. Computers, if you work in a digital equipment, you know that computers or digital cameras don't have that capabilities. In our case, our neural networks have that capabilities as well. So that's why we artificially change the color to basically emulate the illuminant changes, the color, how the color is shifting among the color channels. So that's first key observation. The second is, if we change observers, the labels shouldn't change either. In other words, invariant to observers. And different observers likely have different optical defects. In other words, in computer science, the term is really, if we distort the image in a certain way according to optical formulas, then we still should make our neural networks insensitive to those distortions. So that's another way to do the data augmentation. And then back to the dress. As you can see, once we add in those things, the same different dress or different birds in different color shifting, we feed all those into our training, as the training samples. Over the time, the neural networks develop its own color constancy capabilities by itself, just after training. This effectively turned the 1.2 million training samples into 90 billion training samples. And we have such big machines, we'll be able to handle that big load without any issues. So that's why roughly 2 billion training samples from those 1.2 million give us a neural networks, a much better scope because we see much different variety of the images. One key advantage for doing this is also not just for develop certain, say, color constancy, but also reduce another big problem for big neural networks, that's overfitting. As you can see in this case, because we do all the distortions, neural networks will not see same picture twice. And this time, in this case, neural networks have much less sensitive to overfitting. In fact, this is like 7% improvement right there. And that's some examples. I think the desktop picture was quite striking. Even I, on the first glance, I didn't notice that was the label. Also, according to monkeys, we want to see fine details. So that's where we also work on not just standard images, standard reduced resolution images. We work on the higher resolution images so that we'll be able to get much better detail return and feed that into our model, training model and detection model. And that's the case. If you see the bottom 4 pictures, some very striking examples, and I even myself was quite shocked when I see the example. Can anyone know the first, what is the correct number for the first images? Like this one? Do you think it's a lady, or sunglass, or dress, whatever? We mentioned dress again. Well, it turned out this is a tricycle. If you don't pay enough attention, you will not be able to see the tricycles over there. And one even more striking example is here. If you're into photography, you recognize that brand. I'm doing it, so I know Nova Pro is one of the respectable camera bag brand. But in this case, there is no shape of the bags. There is a logo and also the fabric. Our assistant, once they see enough training samples, actually make that association automatically. They know it is a bag, a backpack, because this is associated with a camera bag. Let's get to more detail to see this tricycle example, just to be more clear. OK, come down to model a little bit. So we always think once you solve the training sample issues, so you're not underfitting, and also you figure out a way to deal with overfitting, then the bigger model, the bigger, the better. So we always try to expand our model because the number of the neurons or number of the non-linearity or number of layers is the potential capability on your networks. So in this case, ours is bigger than the biggest published ones, 40% by 40%. And then also see single model, single crop, you see the performance improvement. And that was the paper when we first published in January, as you have heard twice from both Jason Scalos and Jeff Scalos that mentioned how fast this thing was developed over the time. So that was before January paper, so we get down below 6. That was a tremendous advancement already. But of course, as you already heard, things have changed quite dramatically. So Google, Microsoft, of course, beat us, and Google beat Microsoft. So by today, well, not today, 2 days ago, we are very little bit behind Google. But the important thing is, if you just interpret these numbers by number, that does not mean much. You have to think about what is beyond the number can offer. And this is the example. Our model, because we have all the augmentation, I truly believe that our model is a lot more robust. This just does not occur in the test set. If somebody in this audience or in Italy figure out a way to really distort the images, have a different computation, let's have another run. We'll see who is the ultimate winner. In this case, the first row of the images are from ImageNet. All the image below was either I display image on screen or print on paper, but I use my $100 Xiaomi phone to take a picture. And then you scratch whatever the paper like that, and you fit this picture into our system to do the recognition. Our system gets the result, no problem at all. So that was to show when you add color constancy, when you add the optical distortion, that kind of augmentation, how robust your model can go. Again, this was not in that number, but this in real world is very, very important. Yeah, this is the numbers. When you see this kind of picture, our system can recognize still, no problem. And for ladies, I think ladies recognize this brand, but for us, I don't understand why this is not a towel, it's a perfume. So machine figured that out. I don't understand what is going on. It's beyond my capabilities. And this is another example. That ruler is just so tiny, and in this case, we get it. And for people that eat king's crab every day, this have no problem. But for us, eat pizza every day, then this is going to be a tremendous problem. And of course, this, I think for some people, you know this very well, but I think for most audience here, who don't know what it is. This is the correct label is police van. So this is not lady or not camera, or not a head, it's police van. Now come back to the model. It's not just a model, this is also our design philosophy. Because for us, for doing the parallel computation, when we try to push state of the art, it's our design philosophy is that simple, scalable is all the way to go. All we have to do is really find the key insight that push the performance to extreme. So this is a comparison between our model, which is inspired by VGG work. So VGG was from Oxford University. Right-hand side is from the last year's champion, the Google GoNet work. As you can see, one is very simple, straightforward. Another one is very complex. And that basically reminds you a lot of the preference we showed in the first. So as you can see, both are beautiful, but we have our choices. That's the left-hand ones. Simple, scalable. Now, in summary, we did something quite different than all other people. So that's major differentiators. So we customized built a supercomputer, which will rank around 300 in the top 500 list. But this computer is not general purpose. This is designed for deep learning training. If you put this has to be the fastest in this world. And then we have simple, scalable algorithm plus fully optimized software stack to take the full advantage from underneath hardware. We use larger models. We also, and more importantly, we use much more aggressive data augmentations so that our bigger models be able to see a lot more training samples than others. Finally, we work on multi-scale, including high-resolution images. So that's where we like to point out our approach is brute force, but plus insight. And then once we have that, we push performance to extreme. That's conclude my talk. Thank you.